In this video, we're going to learn how to do basic chemical calculations, sometimes called stoichiometry. As you recall, when we learned how to balance chemical equations, we were counting the atoms and molecules on each side of the chemical equation, the reactants and products side, and we were making sure that all the atoms in a chemical reaction came out the other side. And when we were balancing, the coefficients that we were writing were telling us how much of one compound we would need to use relative to another, but it was written on an atomic basis, on a molecular basis. But in the lab, we usually do two kinds of chemical measurements. We measure mass and we measure volume. We don't directly measure the number of atoms or molecules. Now, we learned a way to deal with some of this when we talked about the mole. And the mole actually allows us to translate from the atomic and molecular bases used in a chemical equation to a mass or a volume basis when we go to the lab to actually measure these things. So, if you look at this chemical equation, one of the examples we've used before, the reaction of aluminum with bromide makes aluminum bromide. This is a balanced equation, so the equation says 2 atoms of aluminum react with 3 bromine molecules to make 2 formula units of the compound aluminum bromide. Now all of this is atomic and molecular basis. However, the coefficients are just ratios. And one thing you can do with any ratio is you can multiply it by a non-zero number and get an equivalent ratio, provided you multiply all the parts of the ratio by the same number. So, if we have a ratio of 2 atoms of aluminum, or equivalent to 3 molecules of bromine, or equivalent to 2 formula units of aluminum bromide, those are for individual atoms, molecules, and formula units. But, remember our mole. A mole is a specific number of things. It's Avogadro's number, 6.022 times 10 to the 23rd. So, essentially, if we multiply the ratio we have here between atoms, molecules, and formula units by Avogadro's number, we get, instead of 2 atoms of aluminum, we have 2 moles of aluminum, or equivalent in the reaction to 3 moles of bromine, which are equivalent to 2 moles of aluminum bromide. So, when you think of the coefficients in a chemical equation, the 2, the 3, and the 2 here, think of them in terms of moles. Now, so the trick is, how do we actually solve a useful chemical problem? So let's propose a little calculation example here. In an earlier video, we demonstrated this reaction between aluminum and bromine to make aluminum bromide. Well, let's say we would like to actually do that live. And we look in the lab and we have 25 grams of liquid bromine that we'd like to react. Well, one of the things we'd like to be able to do is to figure out how much aluminum I will need to actually weigh out to completely react with the 25 grams of bromine. Now you might wonder, well, why do I care? Well, bromine is a rather nasty substance to deal with. It releases noxious vapors, it causes chemical burns on contact. Basically, it's something you don't want to have to clean up after the fact. So, I would like to ensure that the amount of aluminum I add is enough to get rid of all that bromine, which will make my life a lot easier when I need to clean up after the demonstration. So, we know we have 25 grams of bromine that we need to react. So how much aluminum is that? Well, the chemical equation here tells us how to relate aluminum to bromide. It says for every 2 atoms of aluminum, we need 3 molecules of bromine. However, my measurement's not in molecules. So we remember, oh yeah, that's a mole ratio. For every 2 moles of aluminum, there are 3 moles of bromine. The only problem is we haven't measured moles either. We have 25 grams. But we learned pretty early on that to convert between mass and moles, the only thing you need is the formula weight. So the formula weight's easy enough to calculate for bromine. So generally, to solve a chemical problem like the one I've described, you're going to essentially do 3 things. You're going to relate the amount of substance that you know, in this case the bromine, to a number of moles. Now, exactly how you do that is going to depend on whether you know the mass or the volume of the substance. Then, relate the moles of the substance you have to the moles of the substance you're interested in using the chemical equation. So you pull a ratio. In our example, 2 moles of aluminum are equivalent to 3 moles of bromine. You pull that out of the chemical equation because it just comes from the coefficients. And then finally, once you've used that ratio, convert the moles of the new substance, in our case aluminum, to mass or volume or whatever units they ask for. If they ask for moles, we just don't do anything. But typically you'll be asked for a mass or a volume here because you have to go into the lab and measure it, and you can't directly measure moles easily in the lab. So to sum up, to answer the problem that we've been discussing, I have 25 grams of bromine. What I will need to do is convert that 25 grams of bromine to moles. We already know how to do that. Then use the chemical equation, this ratio, 2 to 3, to convert the moles of bromine to moles of aluminum. And then finally, convert the moles of aluminum. In our case, it's probably going to be to mass because aluminum's also a solid, so we probably will go weigh this out on the analytical balance. Now that we've talked about what we're supposed to do, let's actually do it. So, here's the problem written a little more formally. Here's the balanced chemical equation. Here's the problem statement. Given that we have 25 grams of liquid bromine, how many grams of aluminum will we need to weigh all the bromine? Well, we will start with the 25 grams of bromine. We'll need to convert it to moles. And to do that, we'll need the formula weight. So I pulled out a periodic table, and I looked up the element bromine. Now, if you need a periodic table, there's one in OpenStax, and there's also one available for you to print out at the OpenStax, at the scienceattech.com website. Either way, but I looked on the periodic table and I saw that the atomic weight of bromine was 79.90. So Br2 would be 2 times 79.90 or 159.80. Now, one thing you should notice here is that when I calculated the formula weight of the bromine, I did not include the coefficient, because the coefficient isn't part of the chemical formula. It's just there to tell me how many moles there are in this reaction. So don't include the coefficient as part of the formula weight. So let's do the math. We'll start with 25 grams of bromine. This is dimensional analysis, so a times sign and a division line. 159.80 is actually the number of grams of bromine that is equal to a mole of bromine. So I put the formula weight in conversion factor form here, make it a little easier to use. So I want to get rid of the grams of bromine. So put the gram part of the factor, 159.80 grams of bromine on the bottom. Put what it's equal to, moles of bromine on the top. And that gives us, pull out the calculator for a second, 25, since the 159.80 is on the bottom, so divide by 159.80, and I get 0.15644555569 moles of bromine. So we've converted between grams and moles. Now, in case you're wondering about the rounding, I've not rounded this number yet, mainly because I would like to leave the number in the unrounded form in my calculator, because I'm going to use this number as part of the step. Now, speaking of my second step, I want to use the chemical equation now to relate the moles of bromine to the moles of aluminum. So if you look in the chemical equation, what you'll see is that for every 2 moles of aluminum, and that just comes from the coefficient of aluminum up there in the equation, there are going to be 3 moles of bromine. And just in case you're wondering, it does not matter that these are two reactants. You can relate a reactant to another reactant, you can relate a reactant to a product, or you can relate two products to each other. As long as you just pick two substances in the chemical equation somewhere, you can make a relationship like this. So we will copy down our moles of bromine here just to save a little writing, and continue on, times, and a division bar. Now this time we want to get rid of moles of bromine, so take the half of the factor that has moles of bromine, this half, and put it on the bottom. So 3 moles of bromine on the bottom. What they're equal to, 2 moles of aluminum on the top. And clean this up a little bit, put an equal sign. So in our calculator, we take the number we had in there to begin with, times 2 divided by 3, and we get 0.104297,038, and now we have moles of aluminum. So we've converted between the bromine and the aluminum, but we need to weigh out the aluminum, so the number of moles isn't all that useful at the moment. But converting between moles and mass is pretty simple. We know our substance is aluminum, so we go to our periodic table and we look up the atomic weight of aluminum, and you'll find that as 26.98. So what that means is that there are 26.98 grams of aluminum for every mole of aluminum. Now, let's take the number we just calculated, which is the moles of aluminum, put it down here for us to work with, times, and a division bar. We want to get rid of moles of aluminum this time, so we'll take the part of our factor that has moles of aluminum, which is the right side. We will put it on the bottom. Moles aluminum, we'll put what it's equal to, 26.98 grams of aluminum at the top. Clean it up a bit, and then go to our calculator. So this case we're multiplying by 26.98, and that will give us, and now I'll round the final answer because we're done. We need to weigh out 2.81 grams of aluminum. So in other words, if I have 25 grams of liquid bromine to react, I will need to mix 2.81 grams of aluminum with it to make sure that all the bromine is gone at the end of the reaction. Now you might wonder, well, why do you need so little? Well, for one thing, the aluminum and the bromine actually react in a 3:2 ratio. So you only need 2 atoms of aluminum to react 3 bromine molecules. In addition to that, and what's actually a larger effect, is look at the atomic weight, or molecular weight, sorry, of bromine. It's 159.80. So 1 mole of bromine weighs a lot more than 1 mole of aluminum does. So those two things together mean that this number for aluminum should be fairly small. So the answer makes some sort of sense. Now, one thing you might have noticed here is you notice where there's 3 steps. In the first step, we did a little dimensional analysis to convert between grams and moles. In the second step, we took the results of the first step and did a little bit more dimensional analysis to convert between moles of aluminum and moles of bromine. And in the final step, we took the results of the second one and started with that and converted from moles to grams. Well, if you want to make this problem a little bit shorter, because it looks kind of long right now, then you can just realize that all we're really doing is starting with the initial number and multiplying by 1, 2, 3 conversion factors, one right after the other. If you like, you can forego calculating all these intermediate numbers and just combine the entire problem on one line, which makes it a lot shorter, and of course you'll get the same answer because you're literally doing the same work. Now, I suggest when you start solving these problems, do the steps separately first. When you get comfortable with solving problems like this, then, to save space, you can solve the problems entirely on one line. Now, if you choose to do it that way, do not skip this part. Do not skip writing the factors down, because dimensional analysis is a visual method. If you don't write the factors down, then it's actually difficult to set these things up properly, because you lose track of what number goes where. If you have the factors written out, then it's pretty obvious, hey, in my first step, I'm trying to cancel out grams. Let's put grams on the bottom, moles on the top. It makes it a lot easier when those factors are staring you in the face. So always write the factors down. Now, so to kind of sum up here, we have several things we can do to solve chemical problems now. And we've learned before, if we have mass and we need moles, or if we need to go the other way, the thing we are to use is the formula weight. We've also learned that if we have solution volume, say for hydrochloric acid solution or nitric acid or what have you, and we need moles from that, then we want to use the molarity, the molar concentration. And we can go either direction with that one too. The new thing we've learned this morning is if we have moles of one substance and we have moles of another substance, we can relate the two as long as we have a balanced chemical equation. And that's what the little notes down here in the lower right-hand corner are for our next problem, just so we have those things available. My suggestion is these things try to commit to memory as soon as possible, because these are how you solve the vast majority of chemical problems. Basically, you get your information 2 moles, you use the chemical equation to change moles of one thing to moles of another, and then you get that information back out of moles again. So most chemical calculations are 3 steps. Get to moles, use chemical equation, get back out of moles again. Now, let's look at one more example in this video. So, this one, we've taken the training wheels off. We'll have to figure out how to do this one from the beginning. So, here's what they want us to figure out. How many milliliters of 6 molar hydrochloric acid do you need to completely react with 25 grams of sodium carbonate? Here's the balanced chemical equation. And where this problem comes from is it comes from laboratory safety. We use sodium carbonate and sodium bicarbonate to neutralize acid spills. So this question is essentially asking us, if we have 25 grams of sodium carbonate available, how big of an acid spill can we neutralize? So let's figure it out. Now, some advice here before you just start calculating stuff. In a problem like this, you know that it's going to be more than one calculation that you're going to be doing. The problem's going to have more than one step. So my advice is to always start out by figuring out what you're going to do first. So what I like to do is I like to actually write a plan of the calculations I'm going to do before I actually write any numbers down. So you might wonder then, okay, well, how do I start this problem? And the piece of advice for solving chemical calculation problems is when in doubt, convert to moles. That is, when in doubt, convert to moles. Because if you are going to be using a chemical equation like this one, then your information will need to be in terms of moles before you can do anything with it. So let's look at the problem statement and see if there's anything we can make moles. So start reading it. How many milliliters of 6 molar hydrochloric acid is needed? So, can we do anything with that? First, let's ask ourselves what kind of number that is. 6.00 m, this unit right here, that is molarity, which is moles per liter. It's a way to relate volume in moles, but the way you use these relationships down here is you need two of the three things that were listed to find the other one. So if we know the molarity and we want to know the moles, we need to know the solution volume. So do we know the solution volume? No, in fact, we're actually asked to calculate the solution volume. How many milliliters? So to make a long story short, at the moment, we don't seem to be able to do anything with this number right here. So let's continue. How many milliliters of 6 molar hydrochloric acid is needed to completely react with 25 grams of sodium carbonate? Now there's something that we might be able to do something with. So 25 grams of sodium carbonate. That is a mass. And if we want to convert that to moles, we need a formula weight. Now the problem doesn't give us the formula weight, but as long as we have access to a periodic table, we can calculate it. So it looks like the way we're going to start this problem is something like this. The first thing we will do is we will convert 25 grams of sodium carbonate to moles. We will use the formula weight. Now, you could go ahead and do that. There's nothing wrong with it. However, my suggestion is let's figure out the rest of the problem before we start calculating. So, and the reason I suggest doing it now is, remember, these chemical calculations are a sequence. There are 3 steps, 1, 2, 3. And the second step always follows from the results of the first one. So for the moment, let's assume we've actually finished the first step. We found the moles of sodium carbonate. The next thing we would do is convert moles sodium carbonate to, and then we say, okay, what happens when we have things in terms of moles? Well, when you have things in terms of moles, you unlock the chemical equation, meaning you can change one substance to any other substance in the equation. So essentially, we have access to this whole equation. We can take our moles of sodium carbonate and change it to moles of anything else. Now, of course, we're asked for a specific substance here. We're asked for sodium carbonate. So that's what we would like to do next. So we will convert moles of sodium carbonate to, moles. I should have said hydrochloric acid. So the thing we actually wanted was we had sodium carbonate. We want this. So what we'll do is use the ratio. If you look in the equation, the ratio is 2 to 1. We'll write it down in a minute. So let's continue. We're going to convert moles of hydrochloric acid to, and then we say, okay, well, we have moles of hydrochloric acid. What form do we want it? Now we go back to the problem statement. How many milliliters of 6 molar hydrochloric acid do we need? Well, that's a volume, right? So convert moles of hydrochloric acid to volume. And to do that, we would use the molarity. So this is where that 6 molar hydrochloric acid number is going to come in handy. It will allow us to relate the moles of hydrochloric acid we calculate back to the volume. Now once we've done that, we've solved the problem. So now we actually have to do the math. So in our first step, we would like to convert 25 grams of sodium carbonate to moles. We will need the formula weight. So now's the time to pull out your periodic table, because they didn't give it to us this time, so we'll have to calculate it ourselves. Sodium carbonate is Na2CO3. It contains sodium, carbon, and oxygen. Looking up sodium on the periodic table, there are 2 atoms of sodium in the formula. The atomic weight of sodium is 22.99. For carbon, there's 1 atom in that formula. According to the periodic table, the atomic weight of carbon is 12.01. For oxygen, there are 3 atoms, and the atomic weight of oxygen is 16. So going to our calculator, let's clear out some space. 2 times 22.99 plus 12.01 plus 3 times 16 gives us 105.99 grams of sodium carbonate for every mole. I've gone ahead and put it in factor form because that's exactly what I'm going to do with it. I'm going to take 25 grams of sodium carbonate, the amount we were starting with, times, draw a division bar. Since I'm trying to get rid of grams, put the gram part of the factor on the bottom, 105.99 grams of sodium carbonate. On top, moles of sodium carbonate. So let's put this in our calculator. .0 105.99 is on the bottom, so divided by 105.99, that gives us 0.2358713086, and that is moles of sodium carbonate. And I'm going to leave that number the way it is. I'll round it at the end when I get my final answer. Now, so we finished our first step, 1/3 of the way through the problem. For our second step, we will need to use the chemical equation. So if you look at the chemical equation, we're trying to relate sodium carbonate and hydrochloric acid. Now the sodium carbonate coefficient is a 1 here. There's nothing there, so we assume a 1. The hydrochloric acid coefficient is a 2. So this equation says 2 moles of hydrochloric acid is going to be equivalent to 1 mole of sodium carbonate. So, take the amount of sodium carbonate we've already calculated. Here's where you'll start. Times division bar. So I want to get rid of moles of sodium carbonate, so put that half of the factor on the bottom. Moles Na2CO3. Put what it's equal to, the other side of the factor. 2 moles of hydrochloric acid on the top. And clean up a bit. So I need to take the number in my calculator already, multiply it by 2 since that 2 is on the top. And I get 0.4717426172 moles of hydrochloric acid. Now I'm running out of room on this page of our notes, so before we move on and do the third step, let's just quickly sum up what we did. We started with sodium carbonate, and we converted 25 grams of sodium carbonate to moles using the formula weight. We looked at the chemical equation, which related sodium carbonate to hydrochloric acid. We got the relationship, 2 moles of hydrochloric acid is equal to a mole of sodium carbonate. We use that relationship to convert between moles of sodium carbonate and moles of hydrochloric acid. So we're ready to do the last step. So just to give us a little bit of room here, let's do some copying and pasting onto the next page of our notes. So I've copied our directions that we wrote for ourselves, just to give us some place to start. The other thing I'm going to need is I'm going to need the last number we calculated, which is the moles of hydrochloric acid. So we'll start there. Now, to finish up, what we'll need to do is use the molarity. So the molarity, let's go ahead and write down our conversion factor. Now remember what molarity means. The number in front of the big M is the number of moles of that substance that's equivalent to a liter of solution. So when we see 6 molar hydrochloric acid, this is what it means. There are 6 moles of hydrochloric acid equivalent to every liter. So let's use that as a conversion factor. We'll start with the moles of hydrochloric acid from the previous page. We want to get rid of moles of hydrochloric acid, so put that on the bottom. 6 moles of hydrochloric acid down here at the bottom. What it's equal to is a liter. So if we calculate what we have now, I need to take the number I have in the calculator already and divide. Let's see, your calculator is not responding, so you might need to restart the calculator really quick. There we go. So 0.4717 426.172 divided by 6 gives me, and I'll go ahead and round this since this is pretty close to my final answer, 0.0786 liters of 6 molar hydrochloric acid. Now, if all I was asked for was a volume, then this would be an acceptable answer. However, in the problem statement, they specify they want the units milliliters. So we need to do one more thing to give them the answer that they want. And that thing is, we need to convert our final answer from liters to milliliters. Mainly just because it's specified in the problem statement. We always like to give them the answers in the units that they want. Now, in case you're wondering why they might have asked for milliliters, the reason is when you go into the laboratory, in a typical general chemistry lab, everything you measure is in milliliters. So when you work with molarity units, just get used to milliliter to liter conversions. They happen all the time. So, milli is 10 to the minus 3. So a milliliter is 10 to the minus 3 liters. Take your 0.0786 liters, I'm trying to get rid of liters, so put the liter part of the factor on the bottom, 10 to the minus 3 liters. Put what it's equal to, milliliters on the top. And we go to the calculator and we find out, divided by 10 to the minus 3, that our answer in the right units is 78.6 milliliters of 6 molar hydrochloric acid. So if you have 25 grams of sodium carbonate handy, you could actually completely neutralize a 78.6 milliliter spill of 6 molar hydrochloric acid. Now, I have a bit of good news for you. If you could solve this problem, if you can take this problem, write it down on a sheet of paper and solve it on your own, then you can do pretty much any chemical calculation you'll come across. They really don't get any harder than this. So if you looked at these problems and they look doable, then you're in an excellent spot. Although I would certainly recommend practicing with some of the practice problems in the study guide and on the scienceattech.com website. In addition, practice with these problems that we've worked in the video, because you can try them on your own, and then you can come back to the video or the printed notes available on the website and see how you did. In our next video, we'll do a few more calculation examples with chemical calculations. That's all for now, though. Thanks for watching.